Hey everybody, in this video, we will learn about another way scientists determine the ΔH of reactions. But we need to learn about what ΔH of F, or the heat of formation, means. The ΔH of F is the energy or heat absorbed or evolved to create 1 mole of substance from pure elements found in nature, and to be more specific, found most commonly in nature. These ΔH of F's can be negative, 0, or even positive, depending on what type of chemical that we look at. So, for example, in this reaction, we want to find the ΔH of formation for methane, and we want to write a reaction for it. So the reaction must describe something that creates 1 mole of substance from the pure elements found in nature. So in this example, carbon solid, commonly found in nature, and H2 gas, which is the natural form of hydrogen, combine to form 1 mole of methane. So that's how you write the ΔH of formation. Now you might be wondering, what are our natural elements? Well, besides H2, we have quite a few natural elements that have very special characteristics. Of course, we have our diatomic molecules, which are the elements found in pairs, and they include H2, N2, O2, F2, and Cl2 gas. Now, the diatomic molecules that are liquids is bromine, and the only diatomic solid in its elemental form is going to be iodine. Now, keep a note that all noble gases will be considered single atom gases in their natural state, since remember, neon and other noble gases do not react, so they tend to like to be alone. Now, there is also another exception. Mercury, which can be considered one atom, is a liquid at room temperature, so its natural state, which is, I guess, its state found on this planet at a normal temperature, is going to typically be a liquid. Now, every other natural element can be written as a single atom solid. So, for example, if I wanted you to write tungsten in its natural state in nature, then you would write tungsten W and put a solid form right next to it. Now let's do a little practice and write the ΔH of formation for borane, BH3. So to write this, we need to form 1 mole of borane from natural elements found in their natural state. So B, boron, will be found as a solid, as a single atom solid, because it's not part of the exceptions that I listed above. So we could just write B, solid, and notice we only need 1 of them since there's 1 B in BH3. And how many H2s do we need, since hydrogen naturally exists as a gas in its diatomic form? So we would need 3/2 moles of H2 to form 3 moles of H on the right-hand side. And notice how this is a fraction, and we usually don't see fractions in reactions, but this time it's fine because we need to form exactly 1 mole of BH3. So let's take a look at what happens when we double all the coefficients. If we double everything, we will get 2B and 3 H2s to get 2 BH3s. Now, does this reaction describe the ΔH of formation? Well, not exactly, because the ΔH of formation describes the formation of 1 mole of substance, and therefore, this reaction will describe the formation of 2 moles of substance, so the ΔH of this reaction would be equal to twice that of the ΔH of formation for BH3. And why is this? Well, notice how we multiplied by 2, and if the reaction is multiplied by 2, then the ΔH of formation will have to be multiplied by 2, and therefore the ΔH of this reaction will be twice the ΔH of formation, since it's describing the formation of 2 and not 1 moles. So note that difference, and now let's talk about something very special. The ΔH of formation for natural elements is 0. So for example, the ΔH of formation for O2 gas, which is the most common and the most stable elemental form of O, and this will have a ΔH of F of 0, and this is because if you think about it, to make O2 gas from its natural components, you simply take O2 gas and you make O2 gas. Notice how nothing happens here, so this is not really a reaction, but if you wanted to write it this way, you would note immediately that the ΔH of F would be 0. Now, what if we wanted to find the ΔH of F for, let's say, O2 liquid? So, for O2 liquid, it's not the same thing as O2 gas, because if you write the formation reaction for 1 mole of O2 liquid, note that it is formed from the natural components, which is, well, O2 exists in nature in the gaseous form, and notice that this reaction is converting a gas to a liquid. And since this is a phase change, you would kind of remember that phase changes involve something like the ΔH of vaporization, the ΔH of maybe condensation, which is what is happening right here, and those ΔHs are never 0. So the ΔH of formation for O2 liquid is not going to be equal to 0 because it's not the natural form. O2 does not exist as a liquid on this planet. It exists as a gas in this planet. So the gaseous form of O2 will have 0 for its ΔH of F, while O2 liquid will have a ΔH of F that's not equal to 0. So keep a note of that whenever you're working on heats of formation. Now let's talk about something called the summation of heats of formation. It states that the ΔH of any reaction will be the sum of the ΔH of F's of products, considering the coefficients, minus the sum of the ΔH of F's of the reactants, considering coefficients. Now at first you might be like, what does this mean? Well, note that you have to multiply the coefficient of the chemical by its ΔH of F to get the true change in heat for the formation of the chemical, since the ΔH of F describes the heat change or heat energy change for just 1 mole of product. So if your coefficient in reaction is 2 moles, for example, then the heat energy change or the enthalpy change for that will be twice the ΔH of F. And this goes back to the point I made about doubling reactions, and that consequently doubles the ΔH of F, because instead of forming 1 mole, you're forming twice as many moles of product. So be sure to consider coefficients whenever you're doing summation problems. Now, we have to make sure that all the ΔH of formations are in the same condition for this to work. And what I mean by the same condition is that, well, when you're given a table telling you the heats of formation, they're usually at standard condition, which is again 1 atm, 298 Kelvin, and 1 molar. So this concept about the ΔHs being in the same conditions applies to Hess's law too, since all the ΔHs that you add should be in the same condition. The only time you would add ΔHs that are in different conditions is basically when you have no other choice. So we will look at some problems involving ΔH of F's in the next slide. So we want to find the ΔH for this reaction, which describes 2 moles of hydrogen peroxide liquid becoming 2 moles of water and 1 mole of oxygen gas. So I have a table giving us the heats of formation for each of these substances the heat of formation for H2O2 liquid is negative 187.8, and the heat of formation for H2O is going to be negative 285.8. And note that these are in kilojoules per mole. Now, why didn't I include O2 gas? Well, remember, all elements in their natural state have a ΔHf of 0, so this would have a ΔHf of 0. So the first step is to find the sum of the ΔHf's of the products considering the coefficients. And how do we do that? Well, in our product side, we have 2 moles of H2O, and 1 mole of H2O has a ΔHf of negative 285.8. So we multiply these two together to get the enthalpy change, or the heat change, associated with 2 moles of H2O. And we know that we have 1 mole of O2, and since the ΔHf of O2 is 0, that doesn't really matter since 1 times 0 is 0. Now let's find the sum of the heats of formation for the reactants. So our reactants will be 2 moles of H2O2, and the ΔHf for H2O2 liquid is negative 187.8 kilojoules per mole. So now that we have these two, we simply just employ the equation. So negative 571.6 is when you multiply 2 moles times negative 285.8 kilojoules per mole, and the moles cancel out. And notice the 0 just, doesn't exist because it's 0. And we have to subtract that by the ΔHf of the reactants. So in this case, we do 2 moles times negative 187.8 kilojoules per mole. The moles cancel out, and that number gets chugged into there. So the ΔHf of the products minus the ΔHf of the reactants, considering coefficients, will be our ΔH. So we are just simply describing the change, and that's why we have a minus sign, since we're doing products minus reactants, which describes change before and after. So, doing the math, we get that the ΔH is going to be negative 196.0 kilojoules per mole of reaction. And notice that I added that since negative 196.0 kilojoules is the change in enthalpy for the reaction above. And because it's per reaction and not just for any reaction, we have to specify that it's per mole of reaction, so that how many moles is needed to have this much heat released. And notice how I had to include the not symbol, because everything that I did before, I used the ΔHf not, and therefore our answer, when combining all these ΔH's, will have a not symbol, since this was all performed at standard conditions. So don't forget to add the not symbol if all your ΔH's were in terms of the not symbol, which they were. So let's take a look at this. The ΔHf for H2O liquid is not the same as the ΔHf for H2O gas. Now note the difference, and this goes to show that states matter. So let's take a look at what the next slide has in store for us. So in this slide, I am going to prove that Hess's law works. Now, this is just going one step further, but, it's a good way to use Hess's law once again to prove another rule that we are doing. So, let's remember the reaction that we want to look at. It's going to be this reaction. So, the first step is to write out all the ΔHf reactions for each of the chemicals. So we have H2O2, H2O, and O2. So we know that H2O2 is on the left-hand side, and it has to be a 2. So I flipped the reaction, so I had to negate the ΔHf, and I doubled everything, so it's going to be negative 2 times the ΔHf for liquid hydrogen peroxide. So this will be the reaction number 1 that we are going to look at. And let's look at the ΔHf for H2O. So if you remember, H2O was on the right-hand side and it had a coefficient of 2. So all we have to do is multiply everything by 2, and the reaction for reaction number 2 will have a ΔH that's equal to 2 times the ΔH of formation for liquid water. Now, the third reaction we are going to look at is going to be O2. Now, this reaction is kind of redundant since nothing is really happening. So, in the end, we will have to add these reactions up since it's going to be Hess's law, and you will see that many things will start canceling out. So let's get to adding. So, it looks like O2 is on the left-hand side, and this O2 is on the right-hand side, and this will cancel out, and 1 will be subtracted from both sides, so 2 minus 1 will be 1 mole of O2 left over. Now, I notice that the 2 H2s on the left and right will also cancel out. What else might cancel out? Well, it looks like these two cancel out since they're on the left and right, and that's why it was kind of a throwaway reaction since it didn't really do anything to help us. And in the end, we are actually left with 2 H2O2 reacts to form 2 H2O and 1 O2. And this is the net reaction. And notice that according to Hess's law, we add up all the ΔH's, so we end up getting, well, we have to add 2 times the ΔHf for H2O minus 2 times the ΔHf for H2O2 plus the ΔHf for O2, which we know is going to be 0. So this is going to be the ΔH of the reaction in terms of the ΔH of F's that we just derived above. So basically what I just said, and notice that this represents the products, our H2O and our O2, and the reactants will be the H2O2, and notice that the coefficients are all there. So products minus reactants is kind of emphasized here, and we have a proof done. And that's all I wanted to do for this video, so have a nice day.